set of topics. The first talk will be by Shadaj, and he'll be talking about a semantic foundation for progressive stream processing.
Thanks. All right, hi everyone. I'm Shadaj. I'm a PhD student at UC Berkeley, where I work on the Hydro project. And today I'm really excited to share our work on designing a semantic foundation for progressive stream processing. All right, so stream programs are everywhere, used throughout industry for a variety of tasks, ranging from real-time analytics to collaborative editing and even multiplayer games. But the frameworks that we use for writing stream programs vary wildly and have very different semantics that are often incompatible. The most canonical example of a streaming framework is Apache Flink, which uses the traditional model of streams with ordered sequence of elements asynchronously arriving over time. But there are a lot of other systems coming from other research communities that have stream-like semantics but aren't formalized under the same model. Things like Feldera and DBSP from the databases community, which define ways to incrementally process SQL queries over dynamically changing databases. And even things like LVars, which come more from the reactive programming community, focused on ways to consistently query dynamically changing data. And so our goal with Flow is to design a unifying semantics, which can capture the behavior of all these different types of frameworks under a common roof, while providing sufficient structure that we actually give strong guarantees to the developer about how their streaming programs will behave. All right, so the first question to answer when designing a new streaming semantics is, what are we going to define as streams, and what are we going to be doing with them? So the first kind of step that we took with Flow was to broaden our definition of streams to allow for any underlying data type as a collection, going beyond just ordered sequences. Secondly, we preserved the classic piece of streaming systems in that these collections are going to be asynchronously updated over time. And then we have a variety of things we can do with them. In particular, we're going to take the dataflow approach to stream processing, where we're going to take in streams and apply operators that are going to transform them into other streams. And lastly, kind of what makes a streaming program streaming is that we're actually going to be yielding fresh outputs in real time. So when given partial inputs, we want to be yielding partial outputs rather than blocking. All right, so we instantiate this kind of design principles of a unifying data flow language in Flow, which is a data flow style streaming language where you can combine operators that transform streams using sequential and parallel composition elements. The key design principle of Flow, however, is that you bring your own collections and you bring your own operators. So Flow is actually kind of a meta language. We don't provide built-in operators like map or even order sequences, but we provide guidelines and proof obligations for anyone who wants to add these into the language. And so what we're going to focus today is on these elements and the correctness restrictions we have on them. So the first piece of Flow is collection types. As I mentioned, Flow abstracts beyond the traditional definition of just ordered sequences being streams to support many different types. So we support ordered sequences, which are defined by a concatenation operator, which specifies how new data is added to an existing collection. But this concatenation operator can be defined for other data types as well, including sets, singletons, semi-lattices. In the case of singletons, it's kind of a different thing that you might have seen with stream programs before, where you just replace the last value with whatever you're concatenating it with. And this even goes as far as supporting retractions. So this concatenation operator can handle things like removing elements from a set once it's been added. And this is how we use what we use to model things like the incremental SQL engine I described earlier. All right. So now that we've kind of covered the groundwork of how we're going to be structuring our programs in Flow, the main goal of our paper is to define a set of proof obligations and guarantees that we give to the developer about how their program is going to behave. So what makes a stream program good? In Flow, we break it down into two key properties that we think kind of capture the core essence of what developers are looking for when writing stream programs. The first one is a classic property, determinism. We want to make sure that when you feed in the same streaming input, you're going to get the same streaming output. This is fairly straightforward. The second one is a little bit more complicated because it's unique to the streaming domain. As I mentioned before, in streaming programs, we want to make sure that our programs are emitting meaningful partial outputs when given partial inputs. And so we formalize this into a property called streaming progress, which we use to make sure that our programs are actually doing something and not just blocking on input. All right, so let's start with determinism. Now, the most kind of classic way you can think about determinism is at the scope of a single operator, right? If I have an operator like map, again, this is going to be something provided by the user, not something built into the language. We want to make sure that when we provide some input, like 2, 3, 4, the operator may, for example, non-deterministically take elements out of the set in some arbitrary order, but eventually we want to have a deterministic output of the transformation. Now, this might seem good on its own, but as I'm going to show, this is actually insufficient for guaranteeing determinism when you compose operators with each other. To take an example, let's imagine we implemented an operator called fold eager. So fold eager is going to take in whatever partial input it's been received, and every time we re-execute this operator on a growing input collection, we're going to just perform some aggregation. In this case, I'm going to do max. So every time we execute this operator, we're going to take the max of the elements received so far and emit that as a new element of our output collection. So if we imagine some batches of data coming in, 1, 2, 3, 4, 5, 6, 7, 8, 9, in an initial execution, we might just execute it after each batch comes out, and we'll emit the values 3 and 6. But what happens if there's some scheduler delay, right? I have many operators in my graph, and my runtime scheduler may choose to non-deterministically pick which operator gets to execute at different points in the program. And so if we have this delay, we actually see non-determinism in the output of the program just because we delayed when we observed the changes to the input. And we want to prevent this type of non-determinism. So that's where eager execution comes in. So eager execution is an extension to the core operator determinism property that we define in our paper. And the idea is to incorporate dynamically changing inputs into the determinism behavior of an operator. So instead of just being deterministic with respect to a static input, operators are required to be deterministic even in the face of dynamically changing inputs. And the way we we prove this is through this kind of commutative diagram where you have two choices. If I have some new data coming in, I could either process the data I already have, then add the new data, and then continue processing. Or I could add the new data first and then process it all. And we want to guarantee that along both of these paths, we get the same result. So as an example of what this kind of forces the developer to do when they're adding new operators in order to satisfy this proof obligation, we can take a look at LVars. So LVars is this existing work which shows that if you are performing these types of aggregations, it's useful to aggregate them into a lattice where we have a partial order which requires our aggregation to proceed monotonically. So in this case, what we're going to do is use the max function. And so whenever we add a new element, we're going to guarantee that kind of we take the max of the new element and whatever we had aggregated before. The second piece of LVars is it requires us to execute only monotone queries over that lattice value. So in this case, we're going to do a threshold query. So we're going to say emit an event whenever this lattice that I'm accumulating becomes larger than 5. And so in one execution where I execute both operators after every batch, I'll emit the event for 5. But you'll see that even if I have scheduler delay, I still get the same output because of the monotone behavior of this query. And so this operator and its implementation on top of a lattice stream type would satisfy eager execution. And again, the kind of point I'd like to drive home is that these proof obligations are local to individual operators. You never have to worry about how it interacts with other operators. You just need to prove it for each operator you want to add to the language. And we guarantee that you'll get determinism in composition. All right, so now let's move on to the second piece of flow, which is streaming progress. And this is more specific to the streaming domain. So let's take a look at an operator like map. This is a classic streaming operator. I'm going to process each element one by one. And this feels streamy, right? As I have partial inputs, my output is also going to grow because I can just quickly start processing them. But if I take a look at another operator, like fold, this feels fundamentally non-streamy, right? I'm waiting until my stream ends, and then I can emit an element, right? There's no way for me to meaningfully emit some partial output based on this accumulation, where we're blocking on that end of stream. And so especially if the stream is coming asynchronously over the network, I might have this bad behavior where my program might just block indefinitely on this end of stream terminator, which might never show up. Now, if I look at a closely related sibling of fold, scan, Scan is like fold, except as it processes each element one by one, it emits the partial aggregation so far as an output collection. Now this feels streamy again, right? I'm able to emit partial outputs. So we want to formally define a property that allows for operators like scan and map, but disallows operators like fold. And so to define this formally, we actually took inspiration from Flink. So Flink also does not allow operators like fold at the top level over streams. Instead, you have to define these bounded windows to perform aggregations on, things based on time or number of elements. And so we took inspiration from this. So first, in Flow, we introduced the idea of stream termination as an explicit concept. So we introduced this termination symbol, which basically says that all future concatenations to this collection should be ignored. And using stream termination, we actually developed kind of a simple type system that distinguishes from streams that will be guaranteed to bound in finite time and are not guaranteed, may bound. In our paper, we refer to these as bounded and unbounded. And so if we can formally define streaming progress using this type system by taking a look at an operator and looking at its unbounded or may bound inputs. So consider an operator like map. What I want to guarantee is that if I have some partial input, and I let the operator process it all and emit whatever it can, and then I suddenly terminate the input, the output should not change other than also emitting a terminator. Because if it emits something else, that means it was blocking on that terminator to show up. And we don't want the operator to do that. So this provides a very quick check for the streaming behavior. So map, trivially satisfy this. If I add a terminator, the output just gains another terminator, and we don't emit anything else. If I fold, for example, this doesn't satisfy streaming progress, because if I add a terminator, well, then I emit a value, which means that I was waiting until this terminator showed up before emitting my partial outputs. But we actually do allow for bounded collections to perform fold, because I have a guarantee in the type system that it's guaranteed to terminate in finite time. And so we allow this when you have a windowed aggregation. All right, so that's all I have time to walk through today. There's a lot more stuff in the paper that I encourage you to take a look at. In particular, I kind of glossed over this proof that if you have eager execution on operators, that guarantees determinism across composition. It's actually a fairly hairy proof, so I encourage you to take a look at that. The other thing is, how do these bounded streams even show up in the first place, right? If everything's coming in over the network, you might think that everything is unbounded. The way we actually introduce these to the language is through a construct for nested graphs. So you can actually take streams and apply operators like windowing to generate streams of streams. And these inner streams will be bounded and can be processed by smaller graphs with iterative processing constructs. So definitely take a look at that. The other thing I'd like to point out, this is a theory paper, but we've actually put it into practice. So as part of the Hydro project, we've been building a framework for correct by construction distributed systems programming. And we're building things like Paxos in terms of this framework. And the core concepts from Flow, eager execution, and streaming progress actually show up as Rust types in this framework. And so I encourage you to take a look at hydro.run, and you can play around with it today. And with that, I'd be happy to take any questions.
So I'm wondering about this stream when you added the empty set at the end, and then you might output an additional element. What happens for, say, a version of the scan function which outputs like n+1 elements, where you want to output the final value in addition to, like, does that count? Yeah, so currently in the flow semantics, we disallow it. It's meant to be a very kind of quick check that's easy to validate. So we don't allow that type of stuff of like on termination, emit an extra bonus value. Not in the current thing, but we're curious about if there are ways to broaden this property.
Yeah, thanks for the talk. Talking about your operator eagerness criterion, it looks and feels a lot like being a magma homomorphism or something like that, but it seems slightly differently. Can you maybe talk a little bit about the relationship there? Okay, I'm gonna be completely honest. I think
we've not thought too much about the relation. We've had a lot of people come up to us and ask, like the Terminator symbol looks like a left 0. And in fact, our concatenation operator in our paper, we don't require associativity. We don't actually need it for any proofs. It might start looking more like what you're describing if we require those algebraic properties on it, but don't have a very good answer for the relation between those two. Yeah.
So the stuff around determinism because of scheduling, it does smell a lot about like some commutativity going on. So does the foundation also reason about some commutativity?
Yes, yeah, that's a great question. So the place that, so flow itself does not have any commutativity constraints built into the language. We have ordered sequences. Where commutativity shows up is depending on the definition of my collection. So if my collection is a set, then I might have operators that non-deterministically pick elements in different order, which would require your aggregation, for example, to be commutative. I'd actually point you to Hydro. So in Hydro, we have a distributed setting. For example, if you have many machines sending network messages to a single aggregator, we actually encode in the type system that there's message reordering happening there. And that forces the downstream operators to be commutative in order to satisfy these properties. Yeah.
So asking about the earlier property, determinism, it looked like your formulation of determinism prevents turning in intermediate results like in the max case. Is that desirable? It seems like it's useful to know what's the highest number so far, but then I might get a stream with more intermediate numbers depending on how things are grouped.
Yes, this is a good point. So I kind of glossed over this a little bit here. So in the fold case, I was outputting a ordered sequence, or the fold eager case. That's where determinism broke down. If I were to output a singleton instead, I actually would be fine. I would preserve determinism because you would just be replacing the previous values, and the progression leading up to the latest value would be kind of erased, and that's where you have the non-determinism. So depending on the selection of the type that you're outputting, there are ways to kind of do things like emit those early max results. But observing that might be non-deterministic then, like taking a snapshot of that value. So there are tricks you can play, yeah.
Got it, thank you.